like Amanda said, I work on experiments doing measurements of this cosmic microwave background radiation, which I'll tell you quite a bit about today. But we use instruments, telescopes, such as this one that I'm showing here in the title slide, which is the 10-meter South Pole telescope, actually in a photo that was taken by one of our winter rovers who stays all winter taking care of the telescope, continuing measurements at the South Pole. So I'll tell you a little bit about, I'll tell you about, here we go, 3 things. Let me make sure this works. Okay, good. I'll tell you about 3 things today. I want to start out by giving you a little bit of a sort of general introduction to our Big Bang model of cosmology, basically our theory of how the early universe evolved, how the universe began. Then I'll tell you a little bit about these experiments that we work on to actually observe the early universe from the South Pole. And then I'll talk about one of the particular science topics that we're really interested in, which I think is a little bit technical, but it's really cool. So I want to hopefully convey a little bit of why it's so interesting, which is this theory of inflation that we're trying to validate or better understand with these measurements that we're doing from the South Pole. First, let's talk about cosmology. And so I thought, since we're all in this remote world and listening to and talking to people on Zoom, I thought maybe I'd try to break the ice a little bit by asking you a question rather than you asking me a question. And you can just type into the chat what do you think of as questions that we're trying to answer in cosmology? What do you think cosmology is trying to study before I actually tell you about the Big Bang? So if you have some ideas or thoughts about that, we'll take 30 seconds, just type them into the chat and just to get things rolling here. And make sure that the chat works. Okay, good. So we have a few. Oh yeah, here we go. Oh, they're coming in, rolling in fast. So someone says the universe. You're studying the universe kind of as an entity as a whole. That's totally true. Someone said dark matter and dark energy, which are the constituents of the universe. And yeah, that's absolutely right. We're very interested in cosmology and understanding what are the basic building blocks that form most of the matter and most of the energy density in the universe. How the universe is formed, that's exactly what I'm going to tell you about today. How did it begin? Outer space, yeah, but kind of outer space at the largest possible scales. We got a lot more here, so I won't read through them all, but people are kind of getting at the origins of the universe and how this thing, the universe as a whole, sort of the collection of everything we know about, evolves and changes, and what does it contain. And that's all basically right. So I wrote down my answers to this question of what are the kinds of questions we're trying to answer in cosmology, and they're pretty similar to what you just wrote down. We're interested in trying to understand what's the history of the universe, how did it begin, what is the fate of the universe, how will it end, will it go on forever, will it eventually stop expanding and start contracting again. We're interested in this question of what are the fundamental contents of the universe? How much matter is there? How much energy? What are the different types? And if the universe is evolving and changing, what are the physical processes that actually cause that evolution to happen? Why is it expanding, or why is it changing over time? And one point that I like to make about this is that these questions are all actually pretty easy to answer. They're the kind of things that a child might wonder about, like how did everything begin? And you might think that they're like impossible to answer because of that, because they're so abstract, so existential. But what I hope to convince you about is that, in fact, we really do have very definite answers to many of these questions. Not all of them yet, but some of them absolutely we do, and answers that are grounded in careful empirical observations of the universe around us, which to me is really extraordinary and is what makes this field of cosmology interesting and worth studying. So I thought I'd start out going way back to give you a little bit of historical perspective for how we came to our current understanding of cosmology by just pointing out that people have been asking these questions for a long time. Like the Greeks, Aristotle, had their own answers to some of these questions. They thought that there was different physics that operated in the heavens than operated on Earth, because the heavens were more perfect. They had this idea that space and everything outside of the Earth was somehow perfect, and therefore they could predict how things would be based on some abstract notion of perfection. And they had these ideas of 4 elements, not our whole periodic table of elements, but earth, fire, water, and air. And basically, this was not really modern science, but in a few small cases, it did make successful predictions, in particular about the way that planets orbited. And it was kind of one of the first instances where someone tried to write down answers to these kind of basic fundamental questions. So let's fast forward a little bit to around 1910, which is where this field of cosmology really started to take off in a way that was more grounded in empirical observation. And so around 1910, people still had a surprisingly limited understanding of the universe. They actually thought that the universe consisted just of the Milky Way galaxy, and they thought that the universe was kind of static. It didn't have a beginning, and it didn't have an end, and basically you just had stars that were moving around under the influence of gravity, but the structure of the universe was essentially static. And so at this point, this wasn't really a theory in a sense that there wasn't any empirical reason that they necessarily had for believing this was the way the universe was, but it was kind of a reasonable conjecture based on the fact that all their data seemed to say that the stars were kind of all the same. The universe wasn't evolving. But it was really because they didn't have a lot of data that they didn't have a more sophisticated understanding of cosmology. And one of the main controversies that existed in this early 20th century period was something called the Great Debate, or also sometimes known as the Shapley-Curtis Debate, which was answering or asking the question, what are these spiral nebula that people saw when they looked out at the stars with their telescopes? They saw these structures that looked like this image, and which today we know, of course, are galaxies. But at the time, they didn't know that these things were actually separate galaxies like the Milky Way. They just saw these diffuse structures, and they wondered, are these separate galaxies like the Milky Way, or are they just another structure inside of the Milky Way? And in order to actually answer that question, they needed a way of measuring cosmological distances, the distances to these spiral galaxies that were, or spiral nebula that were very far away, which they didn't have at the time until they developed this method of using this type of variable star called Cepheids, which really, this is really the foundation, I would say, for modern cosmology, which allowed us to measure distances to objects and led to, as you'll see in a minute, a large series of additional measurements that changed our view about the structure and evolution of the universe. So this female astronomer, which was very, very unusual at the time, Henrietta Swan Leavitt, made this series of really remarkable measurements in which she showed that the brightness of these, well, first of all, these stars have a variable brightness. If you look at them and you see, and you plot their apparent magnitude, how bright they look, as a function of time, you'll see this oscillation, this curve as a function of time that has a period of a few days. And so Henrietta Swan Leavitt studied many of these stars and was able to conclude that there was a relationship between the period of the star and how bright it looked, which meant that she thought she could use them in order to determine the distances to the star. And so what she did is she studied a large number of these stars that were in a compact object called the Small Magellanic Cloud, which is basically, since it's sufficiently far away from us that all of the stars that are in the Small Magellanic Cloud are basically at the same distance. And she found that there was this direct relationship between the period, essentially, and how bright the star was. But because all of the stars were at roughly the same distance from us, it meant that there was also a direct relationship between the period of the star and how intrinsically bright the star was, because they're all at the same distance. And so what that allowed people to do was to use measurements of the period of these stars to actually infer the brightness, the true brightness, and then correcting for the distance, or correcting. You could infer then the distance based on how bright it seemed, how bright it looked, because you knew at the end of the day that it had what the underlying true brightness was. Okay. So there was this additional step that had to be done in order to calibrate these. So she had a rough calibration for this period luminosity relationship, because she was able to observe a collection of these stars that were in a common compact object, the Small Magellanic Cloud. But this other guy, Einar Hertzsprung, who I think was a Swedish astronomer, was able to use a different method called parallax to measure the distances to a large number of these stars in different places, and was able to therefore calibrate the relationship between the absolute magnitude of the star and its period. So you could use the period to tell the absolute magnitude, how truly bright it is, and you compare that with how bright it seems, how bright it looks, and you know how far away it is, how far away it is to get to dim to the amount that you see. And so just to put, let's see, I'll come back. To put this in perspective, this is what we call the method of standard candles, basically, because you know how bright the star is intrinsically, and then based on how much it is dimmed, you can infer how far away it is. It's like if you have a candle, standard candle, if it looks dimmer, you know it must be further away from you. Okay. Yeah, and I just want to comment actually that Henrietta Swan Leavitt, this work, as I mentioned earlier, was extremely important for early cosmological measurements, and unfortunately, because women were not treated the same in science at the time, she wasn't really recognized for the importance of this work. But many of her contemporaries really did understand how important her work was, and she was in fact nominated for the Nobel Prize by a mathematician at the time, but unfortunately she had poor health and actually died before she could actually receive the prize. So it was a little bit unfortunate, but now we recognize the importance of this work and actually call this relationship between absolute magnitude and the period Leavitt's law in her honor. Okay, so getting back to this question then of whether these spiral nebula are actually separate galaxies or whether they're just structures within the Milky Way, astronomers now had a way of actually measuring distances, cosmological distances. So what this guy, Edwin Hubble, a famous American astronomer, did is he went out and he looked for these Cepheid variable stars in one of the most prominent of these spiral nebula, what we now know as the Andromeda Galaxy. And this is actually a plot of his measurement. He measured the light curve of the Cepheid star, and using Leavitt's law, Leavitt's relationship, he was able to infer that the distance to the Andromeda Nebula or galaxy was something close to about 1 million light years. And this was compared to about the 100,000 light year diameter of the Milky Way. So this is clear evidence that these nebula are outside of the Milky Way, much, much further away than the stars that we see inside the Milky Way. And so this might seem like a kind of minor discovery, but really what this is saying is that the whole universe is much, much, much larger than what people at the time realized. And the Milky Way is not really special in any way. It's one of many, many spiral galaxies that they could see in the sky. So this sort of expanded our knowledge, expanded the size of the universe as we. Okay, so the next thing that Edwin Hubble was thinking about measuring after he had discovered that these galaxies were much further away is he started to wonder whether they were moving towards us or further away from us, and just generally wanted to measure their velocity. So the way we do this in astronomy is by measuring the apparent wavelength of known spectral lines. So you're probably familiar with this Doppler shift effect, where frequencies of light and sound will seem a little bit higher pitched or bluer if they are moving towards you, and a little bit lower pitched or a little bit redder if they're moving away from you. And from measurements that were done on Earth, people knew that hot gas would absorb radiation at fixed frequencies, fixed wavelengths. And so what they could do is they could compare this pattern of absorption lines that they saw in the lab to the pattern they saw from distant galaxies. And based on how much the pattern of lines shifted, they could infer how fast the galaxy was moving away from or toward us. We call this the redshift that we use to measure relative velocities. Okay, and like I mentioned, this is up to a slight technicality. This is basically the same principle that goes on when you hear an ambulance coming towards you. The siren appears a little bit higher frequency than when the ambulance is receding away from you, and it appears a little bit lower frequency. So Hubble did this. He didn't actually do the measurements of the velocities, but he had a friend who was another astronomer at the time, Vestos Slipher. So he took his data he took Vestos Slipher's data and plotted it against his own distance measurements. And he saw that there was this, okay, so the data weren't particularly good at the time, but there was an approximately linear relationship where galaxies that were further away from us were moving away from us faster than galaxies that were close to us. There was a linear relationship between the velocity at which galaxies are moving away from us, and the distance they were. And in particular, at large scales, everything seemed to be moving away from us, which at the time was quite remarkable, was not expected, because people had this idea that the universe was static. And so we can do kind of thought experiments. Think about what does this mean? What does it mean if galaxies that are further away from us are moving away from us faster? So what Hubble's law is telling us is if we have, let's pretend that the galaxies, instead of being randomly distributed, are distributed on a grid. They're points on a grid. And let's say that we're at the red point. What Hubble's law is telling us is that if I go 1 unit away, that next dot over is going to be moving at velocity v. And if I go 2 dots away, that dot is going to be moving away from us at 2v, 3 dots, 3v, and so on. So we can just write that down and then play the movie forward, and at a later time, we'll find that things look like this. In other words, everything is expanding apart from itself, basically. So this is direct evidence that the universe is expanding. The next comment that's worth making, which is also was quite profound at the time, is that it doesn't matter where you're sitting on the grid. Naively you might say, oh, well, if everything's moving away from us, there's something special about our location. There's something preferred about our location because everything is moving away from us. But in fact, if you go to a different point on the grid, you find that it looks exactly the same. I'm going to go to this point on the grid and play the movie forward, and it looks like everything is expanding away from that point as well. So the key point here is that Hubble's law is also telling us that there's really nothing special about our galaxy or our Earth. The universe looks this way from all perspectives. And yeah, there's nothing preferred about our local reference frame. So yeah, the one little minor technical comment I want to make, which you can ignore if you want, but I think it's worth mentioning, is that there is a distinction between 2 types of redshift. So I sort of claimed that the reason that these atomic absorption lines appear to get redder is because of the Doppler shift. And that's true, but you can separate that effect, or that's a distinct effect, from what we call the cosmological redshift, which is due to the expansion of space-time itself. So what's happening here is because space-time itself is expanding, that's the reason why, at least on large scales, galaxies appear to be moving apart from us. Because it's space-time that's expanding, actually the wavelengths of photons as they travel will get expanded. And that is what we call the cosmological redshift, which is a little bit different than the true Doppler shift. In a true Doppler redshift, where space-time isn't expanding, the photon's energy doesn't change as it travels towards us. But because in the cosmological redshift, the photon is actually, its wavelength is stretching out, and its energy is decreasing as it travels across large scales. And that's going to be an important the microwave background in a minute. Okay, so we can do another thought experiment, a little bit more complicated one, to think about what the universe might have looked like early on in the past. So imagine if everything's expanding from us now, then presumably that means that at earlier times, everything was closer together, okay? When things are closer together, they're denser and potentially hotter as well. And if you just keep rewinding that movie, just keep going back and back, eventually the universe becomes extremely dense and extremely hot, and you start having phase transitions in the matter. The universe starts looking completely and totally different. So the first one of these that I'll spend a bit of time talking about, which has to do with this microwave background, is recombination, where the universe was actually so hot that electrons and protons weren't actually coupled together in atoms. The electrons had so much energy because everything was so dense that they actually they weren't bound to the protons in neutral hydrogen. And we'll talk about what happened during that phase transition. But you can rewind even further, and things just keep getting hotter and hotter and hotter, and you start having very, very high energy physics being relevant. And in fact, at sufficiently early times, particles were so energetic that they were significantly more energetic than we can produce in laboratories like at Fermilab or at like the Large Hadron Collider, where we're colliding protons with each other at the highest possible energies. The early universe was actually, particles had significantly more energy even than they do at the LHC, for example. So this kind of leads you to two possible ways of using cosmological measurements. The first idea is that, well, since we understand quite a bit about the way physics works, even at high energies, we can use our knowledge, to try to predict what the universe was like at early times. But you can also flip things around and use observations from physics from these very, very early times to actually learn about physics that happens at higher energy scales than we could possibly study in experiments on Earth. And so that's what I'll talk about at the end when I talk about inflation. The study of inflation actually gives us access to physics that's at such high energy scales that there's no way we could conceivably study it here in laboratory experiments. Okay. So just a word about the cosmic microwave background, because it's an interesting observable, interesting thing to observe. So if you go back to this period around what we call recombination, like I said, the protons and electrons had so much energy because things are so dense that they didn't recombine. And what that meant was that the plasma was opaque to light. If you were to shine a flashlight or whatever, the beam from the flashlight wouldn't go very far before all the light is scattered off of this hot mess of electrons and protons. But as the universe was expanding, and as it expanded, it cooled and eventually formed neutral hydrogen, which is a gas that's clear. We have neutral hydrogen in the lab, and you can shine a flashlight through it and light goes straight through. So what happened then is there were some photons that were buzzing around in this plasma, but once this phase transition happened, once all the electrons combined with protons to form the neutral gas, all those photons stopped interacting, and they just traveled straight through this neutral gas. And they are still traveling straight through, and we can actually observe them today. And that is what the cosmic microwave background is. So when we observe this radiation we're really looking at this glow. It's a pristine picture of this glow from when the universe was in this early state called recombination, which was about 400,000 years after the Big Bang. We're today about 13.5 billion years after the Big Bang. So this is a very early time. Okay. So the prediction is that the universe should be filled with this cosmic microwave background, CMB light, that's left over from this recombination epoch. But early on, this looked like 1,000 degree radiation. So it's like the same radiation that you would see from an electric burner on a stove, except instead of being produced by a hot piece of metal, it's this hot plasma that would be giving off this radiation. But because the universe has expanded so much, that light has undergone this cosmological redshift. It's decreased in energy so that it's now redshifted to a temperature that's about 3 Kelvin, so very cold temperature, and at frequencies that are in the microwave. So about 160 gigahertz, which probably doesn't mean a lot to you, but it's what we call microwave radiation. So we know how to detect it, in other words. And so what you can do if you want to go look for this is you can just get a telescope that can see, or an antenna that can sense microwave radiation, and you just point it out in the sky, and you look for an irreducible background of this microwave radiation, which is coming from all directions, which you really can't get rid of because it's everywhere around us. And so that's what these people did in 1964. So this was a kind of an interesting story. There were these two scientists who were not cosmologists, Penzias and Wilson, who had this very large antenna that you can see shown here. And they actually were not looking for the cosmic microwave background radiation. They were trying to do this experiment where they would send long-range signals around the Earth, bouncing, if I remember correctly, bouncing the signal off of a reflective balloon. And so, as you might imagine, in order to send a signal these long distances, you needed a really sensitive detector, a really sensitive antenna, which is what they had, more sensitive than actually any microwave detector that had been produced at the time. So the way they did it is they had this receiver that they cooled to 4 Kelvin, so very close to absolute zero, with liquid helium to reduce noise, essentially. And what they found is that after they carefully accounted for all of their noise sources, they had this signal that they couldn't get rid of. And they worked really hard to try to get rid of it. They were even worried that there was some kind of radiation coming from, or interference coming from pigeon poop that was inside of this very large horn antenna. I guess this structure was very attractive to birds. And so they cleaned all that out, and they still were left with this signal that was had an amplitude of about 3 Kelvin. These units might not mean much to you, but their noise sources were 0.3 Kelvin. So the signal was about 10 times bigger than the sensitivity of the experiment, 10 times bigger than the instrumental noise. And so what they did is they were basically stumped. And so they called up their friends who were at Princeton down the road. Penzias and Wilson were at Bell Labs. And it turned out that their colleagues at Princeton were doing a similar experiment, which wasn't as sensitive. And after comparing data, they realized that Penzias and Wilson had detected this cosmic microwave background radiation. And this was important primarily because it was the first conclusive evidence for the Big Bang model. It's the first time that we're seeing this hot glow from the early universe, and really the first time we'd seen any radiation from early times in the universe, the first few 100,000 years. And so because of that, this is generally considered the first empirical evidence for the hot Big Bang model. And the other comment that I like to make about this is that it's a good example, which comes up all the time in astronomy and physics, of where technology enables some kind of discovery. You know, it wasn't because Penzias and Wilson were smarter than their colleagues at Princeton that they discovered the CMB. It was really because they had a lower noise receiver, right? And time and time again in science, you find that when someone builds a better instrument, someone builds a detector that has lower noise, or a bigger detector, or whatever, something that hasn't been done before, they're able to see new effects that are often scientifically extremely interesting. And so there's this great link between more advanced technology and a greater ability to do experimental physics that I think is very interesting to see in this case. So for this work, they won the Nobel Prize, not surprisingly, with this other guy, Kapitsa, who did something completely unrelated. But they at least, the Penzias and Wilson at least won half of the Nobel Prize in 1978, a few years later. And since then, there have been a sequence of increasingly more sensitive experiments measuring the cosmic microwave background. So in the early 90s, there was this experiment called COBE, which produced the first all-sky maps of the cosmic microwave background radiation and measured its temperature extremely precisely. It also measured that there were these slight temperature fluctuations in different parts of the sky. So what people had thought before that was that the CMB was, and what they'd observed was that the CMB was basically uniform, had the same temperature as far as they could tell in any direction on the sky. It always looked about 2.7 Kelvin. But with one of the instruments on COBE, they were able to detect that certain parts of the sky, in green here, basically, were a little bit hotter than other parts of the sky in blue by about 0.01 Kelvin. So 1 part in few hundred. And since then, there have been this series of ever better experiments that not only have better temperature sensitivity, but better angular resolution, sensitivity to smaller scale features in the microwave sky. So WMAP, or no, I guess I skipped straight to Planck, which is a satellite that finished taking data in the last couple of years and has produced these wonderful all-sky maps of what this radiation looks like. So just to emphasize here, the hot spots are the red dots, and the cold spots are the blue spots. So when you look in a hot spot, the temperature is a little more intense than when you look in a blue spot, but it's a really small effect, like 1 part in few thousand. Okay, and the other point that's worth emphasizing is now, because of theoretical developments, we understand that these slight fluctuations in the microwave background are really the beginnings of the structure that we see in the universe. All of the stars and galaxies originated as these slight hot spots or slight cold spots in the cosmic microwave background, and then they grew over time as the universe expanded and evolved. The typical, like the typical amplitude of these features turns out to be really, really important to study, because it's determined by the matter and energy content of the universe. So we can actually learn about what the universe is made of by studying this detailed pattern of hot and cold spots. So as you might imagine, the exact pattern of fluctuations that we see appears to be random. So there's this question of, like, how do you compare this random splatter of hot and cold spots with a theory that's supposed to tell you how much matter, or that tells you what they should look like based on the matter and energy content of the universe. So the way we do that is by plotting, and this is a little bit technical, so bear with me for a minute. I'll try to go slow. What we do is we decompose the pattern of fluctuations into a plot that tells us how hot or cold a spot looks, how big of an amplitude the fluctuation is, as a function of how physically large on the sky in angle the spot is. So in this plot, larger scale fluctuations are on the left-hand side, they're over here, and small scale fluctuations, I mean small angular scale fluctuations, are on the right over here. And then the Y scale, the vertical scale, is telling you, like, how many spots there are of that size. So you can, I'll just point this out here. So if you have a big area that looks a little bit hotter than its surrounding area, like maybe this one is a little more red on average than blue, it would correspond to points over here. Whereas if you have a spot that's a little bit red that's much smaller, it would correspond to this peak here. So the fact there's a big peak here is telling you there's lots of spots of this particular size on the sky. And then something that's really tiny that you can't even really see on this picture because it's scaled down too small would correspond to the points off to the right-hand side here. And so, you look at this and you notice there's this funny like ringing pattern where there's a big peak and then a series of additional peaks. And you might wonder, well, why does it look like that? What physics determines the fact there's this big peak, and then why there are these subsequent peaks? So it turns out that this is actually a sign of these oscillations that happened in the early universe. In the early universe, there were these like pressure waves that flowed out from overdensities. And if you can kind of reproduce the pattern in the CMB, if you just overplot a bunch of these shells of sound waves propagating out. So this is a really cool demo that's from this website here, where I'm gonna play this movie, and it's gonna overplot a bunch of these shells of sound waves moving out from spots on the map. And you're going to see that the end result looks kind of like the cosmic microwave background. So you're seeing them overplotting many, and finally at the very end, oh, okay, I got to stop it at the very end. Right now, oh, we'll get there, okay. Yeah, finally at the very end, after you've overlaid a bunch of these shells, you end up with this kind of blobby pattern that looks quite a bit like the cosmic microwave background. And so that pattern of peaks and troughs and wiggles is basically what you get from overlaying a bunch of these shells of sound waves that are moving out from all these different points in space in the early universe. So it's telling us about the physics at this really early time. And that's related to the matter and energy content. And then the other comment I'll make is that so the red points are data, and the green line is a fit to the data with our model of cosmology that depends on the matter and energy content. So the point here is that the model fit to the data is essentially perfect. And that because it's so good, and because the error bars in the points are so small, we can actually very precisely say something about the matter and energy density of the universe. And so the way that works, and is again a little bit technical, but so just the main takeaway you should take from this plot is that the theory prediction changes depending on the constituents of the matter and energy that are in the universe. So if I like dial up the amount of matter, some of the peaks get much higher, some of the peaks don't get as high, and so the fact that some of those values are inconsistent with the data allows us to very precisely constrain the amount of matter, the amount of dark energy, and even the curvature of space-time. And then something called baryons, which are basically the normal matter, the matter that you and I are made of. And so when you do that whole analysis, you compare the data to all these different curves, you end up with a picture that looks like this, where you find that only about 5% of the total matter energy budget in the universe consists of atoms that are like what you and I are made of. Another 24% is dark matter. So it's matter that it kind of behaves like normal matter in the sense that it experiences gravity, but it doesn't interact the same way that the atoms that we're made of interact. And then the majority of the matter energy budget is actually in the form of dark energy, which is something that's driving an accelerated expansion of the universe. And what's remarkable about this is that we don't really know very much about what the dark matter and what the dark energy are. But we know that they exist very well because of the high precision measurements of the cosmic microwave background. So it's this these two things are a very active topic of current research. And I don't have time to talk about them today, but I just wanted to say that's one of the main pieces of information that we've gleaned from the cosmic microwave background is these dark matter and dark energy exist, and we know basically how much of both of them there are to very good accuracy. Okay, so that was a lot of kind of introduction of what is cosmology, how do we know that the universe is expanding, and then why are we interested in the cosmic microwave, measuring the cosmic microwave background. Now I want to talk about actually measuring it. How do we do these measurements? How do we make these maps with the hot spots and the cold spots? And I'll talk about that in the context of the project that I'm most familiar with, which is the South Pole Telescope, shown here. This is a 10-meter microwave telescope that's located at the South Pole. So when you're interested in doing these kinds of observations, the first thing you need to do is you need to fly there. You need to get there. So we go on these very long flights from Chicago, sometimes transferring through San Francisco, and eventually to all the way down to New Zealand, where we spend a few days getting cold weather gear and taking a short break before we take another set of flights on these military cargo planes to a base called McMurdo, which is on the coast of Antarctica, and then another military cargo plane to the actual South Pole. So this whole process, on average, takes about, well, it takes at least 4 or 5 days, and often because the weather in Antarctica is extremely bad, there are frequent flight delays, so we'll often get stuck in McMurdo for weeks or even 10 days. So it can be quite long to actually get to the South Pole. But once you get there, it looks something like this. They have this funny sign at the South Pole, which is kind of cute, honoring these early explorers who first made it there, Amundsen and Scott. That's a long story for another day, but a very interesting one. So the first thing you might wonder is why do we even bother going to the South Pole? What's special about the South Pole for doing measurements of the CMB? And there are a few reasons. First, it's at this very high elevation, pretty high elevation, not super high, but 10,000 feet, that helps. That means the atmosphere is thinner. It has an extremely dry atmosphere, primarily because it's very cold. So they're just really, the air can't support a lot of water vapor. And because of these quirks of the way winds flow in Antarctica, it has very stable observing conditions. The wind is always flowing from the same direction, and the wind flow is always at about the same speed. There's very little turbulence in the atmosphere. The reason we care about it being so dry is for basically the same reason that you use a microwave oven to heat your dinner. And that's because water absorbs microwaves. So if you're trying to observe microwaves from the early universe, and you're on a hot, humid day in Chicago, none of those microwaves will actually make it through the atmosphere, and that's very bad. This is a little bit technical, but it's just showing the transmission, so how much of the microwaves make it through the atmosphere as a function of frequency. And we're roughly interested in observing these frequencies. And you can see, and so this is like the total amount of water vapor in the atmosphere. If you were to take a column all the way to space, condense all the water, this is how many millimeters of water you'd get. And you can see that once it gets up to a few millimeters, the transmission starts degrading significantly. And typical water vapor in Chicago might be something like 50 millimeters, whereas at the South Pole on a good day, it's about less than 1/4 of a millimeter. So, you know, that's another way of saying that is the conditions at South Pole for microwave observations are a few hundred times better than they are in places like Chicago. So you really have to go there in order to do these observations. And there really are only a few other places that come even close: Greenland, Tibet, Atacama, and even they aren't as good as the interior of Antarctica. So what we do is we build telescopes, a few different types of telescopes. So we have these large 10-meter telescopes that I primarily work on, but also some small telescopes that are about half a meter in diameter. So these are like the microwave equivalent of Galileo's telescope, they're refracting telescopes. They don't have very good resolution, but they're a heck of a lot cheaper to build than a big thing that looks like this. So you can build more of them, and that has some advantages for certain science applications. But the advantage of the really big ones is that they give us really excellent angular resolution. So you can see tiny scale features on the sky. And that turns out to be useful for a few different science applications. For example, this is what this experiment Planck would see if you look at a patch of the sky that's about 50 square degrees. And when a South Pole Telescope looks at this same patch of the sky, we see something that looks like this. And so you can immediately start to see the science advantage of this higher angular resolution. Suddenly, all these dots, these white dots and these dark spots become visible. What these white dots are is they're point sources, things that emit lots of microwaves. And there are many types of astrophysical objects that do this. They go by these names like active galactic nuclei, distant star-forming galaxies, transient sources. The point is not for me to describe all these in detail, but the point is just that there's a lot of complex and interesting astrophysics you can learn from detecting and studying the number and distribution of these point sources that emit in the millimeter wavelengths. And you also see these dark spots, which are actually massive clusters of galaxies that are leaving basically a shadow in the CMB. So the CMB is coming from behind them, and the CMB light basically scatters away, or scatters, it turns out, to higher frequencies. But it appears in our data as a dark spot, a shadow. These are really interesting. These are the most massive structures in the universe, and we can detect them out to further distances better than any other technique with these CMB telescopes. Okay. And so just to give you a sense of what the inside of these telescopes actually look like, I'm showing here some pictures of the actual detector arrays. So these are the things that convert the light that enters the telescope into the electrical signals that we actually can measure and record as our data. So over the course of 13 years or so, we've gone through a few different upgrades of these detector arrays. We now are in this phase called SPT3G with 10 times as many detectors operating at more frequencies than we've had before. And I should also just say that this upgrade is something we did at Fermilab. So we actually built this focal plane of detectors. Each of these hexagons has about 1,500 detectors under these little white hemispheres. This was all put together and tested primarily at Fermilab. So we had a big role in this project, which is currently taking data now. And I'll skip over that. These detectors are actually pretty cool, so I'll just say a few more words about them. You know, the signals we're measuring are pretty small. They're not very big, and so you need a really sensitive detector to actually measure them. So what we do is we have behind each of these little white dots, you find a little complicated structure that looks like this, which is a pixel, one pixel, like in your digital camera, although a very different type of pixel. So there's a funny antenna, which is just a normal antenna, sensitive in the microwave, like the one similar to the one that's maybe in your cell phone. And the signals are transmitted from the antenna to these superconducting detectors, which are sitting at 0.3 degrees above absolute zero. So this whole focal plane with all these small detectors is cooled down almost absolute zero, and that's what enables these detectors to be so sensitive. Is they're so cold that just a tiny amount of energy hitting them produces a measurable signal. And the design and testing and optimization of these detectors is a really big job, actually, that we spent a lot of time doing at Fermilab. Okay, so that's kind of a quick whirlwind tour of some of the basics of what these experiments actually look like. And so I want to do in the last closing minutes is tell you about kind of the most exciting of the new physics that we're trying to discover with the current generation of telescopes like SPT-3G and other experiments at the South Pole, which is searching for this evidence of this process called inflation that happened in the early universe. Okay, so if we talked a little bit earlier about how we can rewind the clock, and the universe gets hotter and hotter and denser. But if you go way back to the earliest possible time that we have even theories about, you end up hitting this period called inflation, where we think that the universe expanded exponentially by an enormous amount. And let's see. The reason why we think there was this period of inflation is because of a couple problems that people realized from early measurements of the CMB. So the first one of these, which I like because it's pretty easy to understand, is called the horizon problem. And what the horizon problem is basically saying is, or wondering, is why is the CMB so uniform? I showed you these images where the CMB was uniform to 1 part in 10,000 or 100,000. In other words, that part of the sky looks the same as that part of the sky. But if you think about it for a minute, it's not necessarily clear why that should be the case, right? The photons from these 2 patches of the sky in opposite directions are just coming into contact now, today, as we observe them. So how could they have possibly known what temperature the other one was at early times? If they're just coming into what we call causal contact, they're only just able now to communicate with each other. And so in the standard cosmology, that shouldn't actually be possible. So that's one problem. That's the horizon problem in a nutshell. The CMB is extremely uniform, but there's no way that different patches far away from each other should have been able to communicate and know what temperature the other was at. There's another more technical problem called the flatness problem, which I think is worth mentioning because it has to do with well, because it's interesting. So space-time can be curved, as it turns out. It can kind of be like a sphere, or it can have this kind of saddle shape, which basically has to do with whether the angles of a triangle add up to 180 degrees or whether they add up to more than 180 degrees, like they do on a sphere, or less, like they do on a surface that has negative curvature. And so in the model of the expansion of the universe, basically the curvature always should grow. It should always get bigger over time. But empirically, we observe that the universe today is very, very flat. It's very close to being the case that the three angles of a triangle add up to 180 degrees. So if the curvature is always growing, that must have meant that the universe was even more flat in the past. And why should the universe be so close to being perfectly flat? There's not really a clear reason for understanding why it should be so perfectly flat. Okay, and I'll skip this. Right. So the solution to this problem is this period of inflation, where we think that the universe expanded exponentially between the periods of roughly 10 to the minus 36, 10 to the minus 32 seconds after the beginning. So incredibly early times. And the universe expanded in the theory of inflation, we think, by a factor of something like 10 to the 26. So this is an enormous number. I think it's something like roughly inflating like a yardstick to the current size of the observable universe in this infinitesimally small fraction of a second. So this is a really extraordinary process. The expansion was happening faster than the speed of light. And what that does is it effectively solves this inflation problem, solves this horizon problem. And the way you can think about that is basically, if you imagine this red circle being all of the points that can be reached by a message sent at the speed of light, those are all the points that should be in causal contact with each other. But if and these points on the grid, you can imagine as like, observers or whatever in the background space-time. So if I inflate the space-time extremely, extremely rapidly over a short amount of time, the red circle doesn't grow that much. The red circle is not growing very much because it's set by the speed of light, basically. But the background grid can expand faster than the speed of light. And when you do that, you can push the points, push the observers to make it look like they never could have communicated with each other. They're outside of the red circle. But in the past, when everything was much closer together, they could have communicated. So the idea of inflation then is that if at early times, everything was in thermal contact, it was in causal contact. That's why that part of the sky knew what temperature that part of the sky was at. They were actually connected. They could send messages to each other at the speed of light. But then you inflate the universe very quickly, and it looks at later times like that part of the sky was never in contact with that part of the sky. So everything was in causal contact early on. After inflation, things fall out of causal contact, but still at early times, they could have communicated with each other. That's the trick of inflation, and that's why it solves the horizon problem. It also solves the flatness problem, but I won't go into that because it's a little more technical. Right. So you might then ask the question, okay, this is like very abstract. You've talked about inflating points on a grid. How could you possibly test this, especially since we're operating, or we're saying that this process is happening at these absurdly early times and extremely high energies? How can we actually look for evidence of this process, and why is it not just speculative nonsense? So it turns out you can, using the cosmic microwave background. And to understand why, we have to go on a little bit of a digression, but not too far. So you guys may be familiar with the fact that light is polarized, which is to say that light waves have a certain direction associated with them. And you can filter out the different directions with a special type of filter called a polarizing filter. And this is the principle in polarized sunglasses, which maybe some of you have or have used, or a polarizing filter on a camera. So an example of what this does is shown here. If you look, the light that reflects off of the surface of a pond, for example, tends to be preferentially polarized in one direction. So if you look at it through a polarizing filter, you're able to block the reflected light off of the surface. And photographers use this so that they can actually see more of the features beneath water, for example. Or you might use it when you're driving on a sunny day where it's just rained, so that you don't get blinded by the reflection off of the road, which is preferentially polarized at some level. So it's the same deal with the CMB. CMB is actually polarized at about the 10% level. So what that means is you can go out, if you have a polarization sensitive detector, you can go out, point it at a particular direction, and there'll be a slight, on average, a slight preference for light of a particular polarization angle at different parts of the sky. And so it turns out that so the CMB kind of has a random looking polarization pattern. And it turns out you can split it into two senses of polarization. You can split it into something we call an E mode pattern, which is like a star well, it's things that look like this. So it's a star shape or circular pattern, and B modes, which have a curl to them. They're kind of curling out from a particular point. And so this is just an example shown over here of what a pure E map and a pure B map look like. And you might, if just glancing at these, struggle a little bit to tell them apart. But if you look at like this feature, you can kind of see that all of the angles, the polarization angles, are wrapping around in a circle. And if you look at like maybe over here, they're kind of all diverging away from this point. Whereas in the B modes, you can see there's more of a twisting pattern to it, where these points are kind of curling around outside of this localized area. Anyway, the point is that inflation affects the way the polarization from the CMB looks. And the inflation is really the only process that can produce these B modes on large scales on the sky. So if you go out and make maps of the polarization and you see B modes, at least on large angular scales, that is a direct evidence that inflation happened. And so that's what we have been doing with our recent experiments. So this is another way of plotting, another plot of that those ringing patterns that I was showing you earlier. So you can make a similar plot with the ringing patterns in E modes, and also for the B modes, which are at smaller amplitudes. And on these large scales down here, with where this red box is, would be where you would see these B mode patterns for inflation. So there are other mechanisms that are at much smaller scales over here that can produce B modes, but down here, there's really no other mechanism at these large scales that will produce B modes. And these are extremely difficult measurements to do, basically because the amplitude of this signal is very small. We're way down on the bottom of the plot. And so you have to build many detectors with many telescopes to actually try to see these B modes. Okay, and last slide, I'll just say that this is what we're doing. So this is actually a little bit of a technical slide. I copied it from one of my more technical talks, but we are trying to build, instead of one telescope, we're trying to build many telescopes. Instead of just at the South Pole, we're trying to do it in the South Pole and in Chile, with these two different types of surveys to look for both inflation as well as some other topics that I don't have time to tell you about today. But we have these we're planning to build these large telescopes with these enormous cryostats. So this is actually this is wider than I am tall. This is like 3 meters wide, with over 100,000 detectors that are all cooled down to this tiny fraction of a degree above absolute zero. And then we'll have many of these smaller, more Galileo-style refracting telescopes also located in the South Pole. And the idea here is just to keep making progress. We need to have more and more detectors with more and more telescopes in order to improve our sensitivity, lower the noise of these measurements. Okay, so I'm already a few minutes over, so I'll stop here and just say, if you're gonna, we talked about a lot of stuff. Maybe I talked about too much stuff, but if you remember anything, I hope you remember these 4 points: that the universe is expanding, and it started out with a Big Bang. We've done this long series of experiments that have performed precision measurements of the cosmic microwave background. And with the experiments that we're doing now, we're testing physics really at unbelievably early times and ultra high energy scales, much higher than we can access in the lab. And there remain these fundamental open questions that I haven't talked about, I didn't have time to talk about today, but a lot of cosmologists are working on to try to understand what is the dark matter, what is the dark energy, and we, people measuring CMB, are very interested in this question of did inflation happen, and if so, what is the physics that caused it to happen? So I think I'll stop there. We can ask, we can take questions now. I think I missed a couple of questions. Maybe I missed one question. Someone was asking. So someone was asking if galactic clusters are uniformly distributed, or are they randomly distributed throughout space? The answer here is they're randomly distributed with a particular distribution, by which I mean there tend to be clumps of them of a certain size. They're not completely uniform, and you can predict what that clumpiness pattern should look like from models of cosmology, and then compare the measurements of the clumpiness to those models. And so yeah, so it's uniform. It's random, but with a non-uniform distribution, if that makes sense. There's another question here about downloading slides for review after the lecture. Yes, I can put them in a PDF, and if I can post them online if Amanda can help me with that.
Absolutely, absolutely. Also, there's some great questions in the chat, but I also, you know, if you want to ask a question verbally, if you open the participants window, there's a raise your hand feature, and we can unmute you and you can ask a question that way too.
So maybe I'll just go through a few of these questions that were typed into the chat, and then maybe take a few from the hands that are raised and then go back and forth. Okay, so someone, Ritika, asked a great question, which is, how do you cool down detectors to almost absolute zero? And there are actually a lot of different ways to do it. We use two techniques. So actually we use three techniques. So we first have something that's called a pulse tube cooler, which cools everything down to about 3 or 4 Kelvin, 3 or 4 degrees above absolute zero. And a pulse tube cooler is actually the same thing that cools a magnet in an MRI machine. So if you've ever had an MRI scan of some part of your body, you might remember there's like this pinging sound that you heard. That is the pulse tube cooler, which is cooling the magnet. We use the exact same, well, basically the same technique to get us to 4 Kelvin. And then we have one of 2 different types of refrigerators that get us down to a fraction of a degree. And both of them use, in slightly different ways, helium, 2 isotopes of helium, helium-3 and helium-4. One type uses basically evaporation, so like the same principle that is why you cool off when you sweat. The sweat evaporates, that cools you. And then another one uses this more complicated thermodynamic property of mixtures of helium-3 and helium-4 that gets a little bit colder. But those are the techniques. Pulse tube to get to 4 Kelvin, and then some way of manipulating helium isotopes will get you to a fraction of a degree. Jonathan asks, what universities are involved in this research? That's a great question. So our particular experiment has quite a few universities. The main institutions are University of Chicago, Fermilab and Argonne National Lab, and then Berkeley, University of California in Berkeley. And then we have people at a few other institutions, I think UCLA, Case Western Reserve University. But I should say that there are a number of experiments similar to ours. And so research like this is going on at many, many universities. Certainly, I would say all or most of the major universities in the US, top universities, have some people working on this kind of research. Someone says she was a former lab employee a long time ago and didn't know they did work like this at the lab. Yeah, it's actually relatively new. So this program at Fermilab, studying CMB, has only really been around for 5 years or so. So this is a recent development for us, although people have been doing this for a long time. Ben asks, are there plans for satellites to help in cosmic background radiation research? Will the James Webb Telescope have any detectors that will be useful for this area of research? So for those of you who don't know, the James Webb Telescope is this very expensive, elaborate telescope which hasn't launched yet, but targets the infrared radiation. So just a little bit at frequencies a little bit below the visible. And so the James Webb Telescope won't actually be sensitive to these microwave observations. So it won't help us so much directly. There are some plans for CMB satellites, but I would say that none of them have been funded. So there's at least one proposed mission in the US, which is kind of at a concept stage. And then I think there's one concept mission maybe in Europe. There is actually a Japanese, sorry, I misspoke. There's a Japanese satellite mission, which is supposed to launch in 4 or 5 years from now, I think, and has some American involvement. It's called LITE, L-I-T-E, BIRD, but it's still in pretty early stages of development, I would say. Okay, so Rushil says, how do quantum fluctuations relate to CMB? Do they interfere with the CMB? So this is a good question. So for those of you who may not know what quantum fluctuations are, at very early times, because of kind of the uncertainty principle of quantum mechanics, there were random fluctuations in the positions of particles and density of particles. And basically, those random fluctuations, which are kind of the result of quantum mechanics, for lack of a better word, there's very small random fluctuations in the density of the universe at very early times, are actually what seeded the fluctuations that we see in the CMB. So it's like those initial tiny fluctuations got blown up in scale by inflation when the universe expanded really, really rapidly early on. And then over time, those fluctuations grew, and that's what seeded the hot spots and the cold spots in the CMB. So to say that they interfere with the CMB is maybe not quite right, but they are what produced the fluctuations in the CMB. So we're not looking at them directly, but we're looking at fluctuations that have been processed by this oscillation, baryon acoustic oscillation that I described at much later times. Okay, so we go, okay.
There is someone with their hand up. I don't know if you want to take a look.
Yeah, let's take 1 or 2 people with their hand up, and then I'll go back to these because there are a lot of questions in the chat.
Okay. Ben?
Hi. Can you hear me?
Yes.
I just recently started learning about like Hawking's no boundary proposal, and I was curious, like, is it absolutely definitive that that's garbage and there was 100% a Big Bang, or is this something that's still viable and being researched? Like perhaps it could help figure out like the inflation problems and the flatness problems. And I don't want to become a mathematician or anything, but maybe like steer me in the right direction of where I could do some more research into this.
Yeah, so to be honest, I'm not familiar with this Hawking boundary problem. Is that what you?
Yeah, it's the no boundary proposal by Hawking, and I forgot who he collaborated with, but basically instead of a Big Bang, all time was consolidated into, there was only space, so it was only one variable. So instead of like that original picture you had where it looks like a shuttlecock with a point at the tip, it's just a rounded off shuttlecock, like a, you know, like a birdie in badminton. And I think it's rather fascinating.
Yeah, so I should say that I sort of made it seem like inflation, there's no alternative to inflation. So I'm not familiar with this exact proposal, but there are a couple of other alternatives to inflation. There's one that's called like the epchirotic universe, where I'm not extremely familiar with it, but the principle is something like the universe expands and contracts kind of forever. So there are these alternatives to the standard inflation and lambda CDM cosmology. And I would say that in general, I think that there are issues with them, like either theoretical issues or empirical observations that they don't quite match. But it is true that you know, there may be alternatives to this, certainly to this inflationary paradigm that aren't as widely studied, but I think are not necessary. We don't know that they're wrong at this point.
Thank
It's
you.
an interesting area of research. Yeah. Does anyone else have their hand up right now? Otherwise, I'll go back to the.
Yes, there's one more with their hand up. I'll go ahead and.
Okay, let's do that one.
Yeah.
Hi, I had this question in the chat, but you don't have to answer it there. I asked if all matter in the universe is moving away from each other, is like the space between atoms also expanding, and what would be the outcome of that?
Yeah, that's a great question. So you could imagine if you fixed the location of if the location of every atom were fixed on this background grid and you expanded it all together, then like we would be expanding, like our bodies would be getting bigger over time. So that's not what happens actually. So, and the reason for that is that atoms are bound to each other by like electromagnetic forces. And you know, the size of the solar system is fixed because we are gravitationally bound to the sun. So it's really on very large scales, like between gravitationally bound objects, that this expansion is relevant. The space between the pairs of atoms inside your body aren't getting bigger. Yeah, that's an important conceptual point. Okay.
I think we can go back to the chat questions.
Great. Oh, so this is a good one. Why does the brightness of Cepheid stars vary? So I should say I'm not an expert in Cepheid stars, but I do know why this works. So basically what happens is it's a feedback process where ionized helium. So ionized helium is opaque. Light scatters off of the ionized helium, and so in the outer atmosphere of these stars, there's a lot of this ionized helium, and it heats up. So the star expands because the helium is getting hotter, and as it expands, basically the optical depth. Well, as it expands, it cools off again. And so once it cools off sufficiently, it starts to contract again. And so the actual atmosphere of the star is oscillating. And that oscillation results in a variation in the transmission of the atmosphere and a variation in the apparent brightness of the star, because the ionized helium basically has some opacity to it. So in addition to the brightness varying, the physical size of the star is oscillating in and out with a period of days, basically. Okay, so the question of, will gravity win out after stars burn out? Will that somehow negate dark energy? Will we then have another big bang? So the answer is no. At least as far as we know, dark energy will win out and the universe will continue expanding forever. And the right way to think of it is a little technical, but basically dark energy is an energy that's associated with vacuum. So like as the universe expands, the total amount of dark energy, the density of dark energy doesn't dilute, it stays the same. But the density of normal matter does dilute. And so as time goes on, basically dark energy always wins out over the gravitational pull of the, or the gravitational effect of the normal matter or the dark matter. So question is, the next question is, what causes the temperature fluctuations of the CMB? So this is a great question. So as I mentioned, I think a few minutes ago, the fluctuations are seeded by these very early quantum fluctuations, and then those fluctuations grow over time because of a bunch of different physical processes. But one of those processes is this baryon acoustic oscillation. So the idea here is that at overdensities, matter tends to infall, and then the matter in the plasma heats up a little bit, and it sends out these pressure waves, and that process, and then these waves basically oscillate. And that process of early fluctuations processed by baryon acoustic oscillations are what give the CMB its many, not all of, but many of its characteristic features. And there are a lot of subtle points there that I've glossed over, but that's the main visible feature in the CMB is this baryon acoustic oscillation process. So the evidence for inflation is strong, but is there a mechanism to explain how it happens? Yeah, yes and no. So there's a mechanism that explains how it happens that involves adding another particle basically to our model of particle physics that undergoes a phase transition early on, and that phase transition releases a bunch of energy that causes the space-time to expand. So there's a model for that you can write down, but it comes at the price of adding another particle that whose existence we haven't confirmed or don't know about. So I would say that we kind of understand roughly the physics of how that process happens. There's a lot of uncertainties though, like you can have inflation models where you add additional particles, and in general, you can write down many different types of particle physics models that will produce the same process of inflation. And so people often criticize inflation for not really being a theory. It's more like a class, I guess, of theories. And it's relatively difficult to think of a way to tell apart different models of inflation. But we do kind of roughly, we have there's a specific model or class of models that does produce the inflationary process that is understood reasonably well, with the caveat that it involves inventing particles that we haven't detected yet. So there's another question that says, is there data to support multi-universes? So this is something that I'm really not familiar with. I think the answer is, I'm pretty sure, is no, that we only know of one universe. We only have data that, we don't have data that there are multiple universes, but there are people who speculate about maybe there are multiple universes, or universes somehow branch apart. I would say this is all highly speculative, and there aren't many good leads about how you actually experimentally decide whether those theories are true or not. But people do think about them, and it's kind of interesting as a thought experiment, maybe. So Sean asks, are there any new technologies that are helping colliders reach a level of heat close to the Big Bang? I would say that, at least in our lifetime, there's no hope of colliders like the Large Hadron Collider or its successors getting to the kinds of energies that are relevant at inflation. So yeah, there's a ton of technological development on how to build higher energy colliders, but those technological developments will only get you, another factor of 10. They won't get you a factor of 10 to the 12. So there's a big gap between what we can realistically do in terrestrial experiments and what we could conceivably ever do in our lifetimes with colliders. How long can a red dwarf star burn? This is a question Mike asks. And I'm going to concede that I don't actually know the answer. I'm not really an astronomer. I'm more of a physicist, and I'm actually not familiar with lifetimes of red dwarf stars. So maybe you'll have to look that one up. Sorry. So let's see. Jack is asking about ideas of Roger Penrose. I'm not entirely sure which ideas, so I'm not sure I can answer that one either. You're referring to. Susan is asking, could there be dark matter in us and in everyday objects here on the Earth or in the Earth's atmosphere? So this is a great question, and the answer is yes on both counts. We don't know what the dark matter is, but one of the most compelling candidates for it is that it's some kind of particle that is weakly interacting, that really is, you can think of it as kind of a gas that permeates everywhere in the galaxy. But because it's so weakly interacting, these particles would be just passing straight through us without ever interacting, or interacting extremely rarely. Excuse me. So I think in that paradigm, which we call this the WIMP, the weakly interacting massive particle, in the WIMP paradigm, or the WIMP models, yes, the dark matter is passing through us all the time, and passing through the Earth, passing through everyday objects, passing through the atmosphere, and we just don't know it because it doesn't interact with us. Or if it does, it interacts extremely rarely. And what one type of experiment that people have been working on for a long time is building extremely sensitive detectors, which they put underground in order to shield them from cosmic rays and other radiation, which are really sensitive. And they're looking for very, very rare scattering of a dark matter particle off of an atom in the detector, whose recoil they can then detect. So that's an important principle behind this whole industry of experiments that what people are doing, is the fact that the dark matter can pass straight through us. There are other types of dark matter, other models that look different than that, but that's the one people focused the most on because it's the easiest to actually measure, go out and detect.
I was just kind of looking at time if you want to take one or two more questions from the chat.
Yeah, I'm gonna zoom through here. Okay. Okay. So someone is asking, how do you use the, sorry. Okay, here's a good follow-up to the dark matter question. So Mike is asking, does dark energy and dark matter consist of atoms not on the periodic table? And there are two parts to this question. The answer is, the first part is, are the dark energy and dark matter conceivably one of the elements in the periodic table? And the answer is no. We know that is not the case, basically because if they were, they would behave gravitationally like the normal matter. They would also interact electromagnetically with light, and they don't behave like that. So we know they're not normal types of atoms. Now you could also ask, well, like the dark matter, could it be like a dark atom? Could it have some complicated substructure, consist of different types of particles that are bound together like an atom, but where the individual particles aren't protons, electrons, and neutrons? And the answer to that question is yes. We don't actually know if the dark matter has some kind of molecular or atomic substructure like normal matter. And indeed, it would not be crazy to think that the whole dark sector, all the dark matter, would have as complicated interactions as all of the normal matter. Like normal matter is really, really complicated. Like the whole periodic table is a very complicated thing. And it would be sort of strange, actually, if most of the matter, which is the dark matter, didn't have any of that complexity, and it was just one type of particle. So people speculate a lot about, have speculated a lot about the types of substructure or complexity that the dark sector might have. But unfortunately, we don't, since we haven't detected it directly in the lab, we have a very difficult time understanding which of those models is true, and understanding what types of substructure are more realistic than not. So people haven't, I would say people haven't explored the full complexity that the dark matter might have, but it would be a little bit strange if it were extremely simple, just given that normal matter is quite complicated in how it can arrange itself. And I think we're probably out of time, so maybe I'll just end there.
Yep, that sounds great. So I want to thank everyone for joining us for our talk, Looking Back in Time, Cosmology at the Beginning of the World. Thank you for joining us, and I want to thank Dr. Anderson for giving this lecture and answering our questions. I hope to see you at future sessions of the Summer Science Series. You can find more information about that by following us on Twitter at Fermilab Ed, on Facebook, and also on our website, ed.fnal.gov. So again, thank you for joining us, and we hope to see you at another session.
Yeah, and thank you for all the great questions. This went very well.